which is going to be in Nearpod. So if you look at your shared screen, there's a code there, and you can just go to Nearpod, enter it. And the warm-up is just if you look at item A and you look at item B and you compare and contrast, how would you compare and contrast? So what's the same about them? What do they have in common, which is what comparing is? And then how are they different, which is contrast? So go ahead and take a look at that. Enter the Nearpod and let me know. Let me know what you think. All right. So I think that's about enough time for this. It's 1:34. So we've been in class for 4 minutes at this point. So if you have not already and you are here, welcome. And please go to join.nearpod.com and enter the code QWL6Y so that you can join our Nearpod, because I'm going to move off of this in just a moment. Okay. All right. So everyone's got that code QWL6Y. Great. So here's what we're doing today. We are in a new unit. We are going to find limits of infinite sequences by recognizing the end behavior of the underlying function. And we're going to use summation notation to describe a series. So this unit, it's not as pretty as polar curves. It's not as attractive as polar curves, but it's interesting because you do get the, you do get sort of that satisfaction of looking at a pattern and figuring out what the limit behaviors are, which does carry some satisfaction in it. So we're doing the warm-up, framing learning now. This is going to be notes mixed in with check-ins, and then we'll do a summary and a check for understanding. Okay. We have the homework published, but I'm waiting on the formative. I don't want to publish the formative until we've had our second class. So I'll publish that formative probably Thursday afternoon. And then it'll be due next Wednesday. Week 5 stuff is due Wednesday, and then you can still make up weeks 1 through 4. However, if you are a senior, and I think I only have 1 or 2 in this class, Wednesday is your last day to turn stuff in. So your last day of class is the 28th, but the grades close on 5/26. I have been calling home for not just seniors, but everybody who is failing. So I've started making those phone calls. Please fix your grades, turn stuff in, do your work, do what you need to do. Also, if Synergy didn't import a grade correctly, please email me, please let me know. Because otherwise I'll check, but I know Synergy has been acting up. I know there have been problems in the last couple of weeks. So if you see that you got, 20 out of 20 in Canvas, but I'm missing on Synergy and I haven't fixed it, please let me know and I'll fix it, okay? I've highlighted in Nearpod, I'm gonna go ahead and go forward in the Nearpod now. I've highlighted this capture sheet. So if you want, today we have a capture sheet because I'm going to be doing a lot of writing on the document camera. So if you want to, where this is highlighted and hopefully everybody's in Nearpod at this point, click on capture sheet and open it, and you should be able to make a copy and go from there if you want the capture sheet, okay? Okay, are there any questions, any points of confusion or concern at this moment? Okay. So in that case, let's go back to the capture sheet. So I'm going to go to sharing the document camera for a bit. All right, so hopefully you see this is the capture sheet that you might want to use. If you can use it, feel free. If you can't use it, and you want to take notes, that's fine too. But your responses to the warm-up, I could just kind of put them, summarize them into, distill them down into basically a few key points that you all made. So I think everybody noticed that the graph and this item A and item B, were decreasing. And some of you noticed that it was decreasing by the same interval or same amount. So that was interesting that you all noticed that. And then the contrast, most of your answers for the contrast were that item A was a graph and item B were points or numerical objects, right? So that was most of the contrast that I noticed of people making a note of, okay? So what's interesting, they are decreasing by the same interval. So here we've got the function is living at 8, right? Now it's living at 4, now it's living at 2, 1, 1/2, and so forth. So it's basically, this function is decreasing by half every time n increases by 1, okay? And there's a formula for that. This is a function. This is f of x equals 1/2 to the power of x, right? It has a domain of all real numbers, and we have studied these before when we're studying exponential functions. It's a graph 1/2 to the x, okay? Item B is kind of similar, except it only takes a few values, right? We don't take all the in-between points here, right? This is a continuous function. You can have 1/2 to the anything. You can have 1/2 to the 3.2. You can have 1/2 to the 3/4, right? But this is just very, very specific. This is basically this function, but when x equals 1, when x equals 2, when x equals 3, when x equals 4. So this is a sequence, and we're going to use different notation for this. This is a sequence, still sort of in that same function notation, and it still has the pattern 1/2 to the n, but the domain is natural numbers and not real numbers. The domain is natural numbers and not real numbers. So for example, 1, 2, 3, 4, and so on. It's the same function, but we don't take decimals, right? We're just taking 1/2 to the 1, 1/2 to the 2, 1/2 to the 3, 1/2 to the 4, okay? So good job with the warm up. And then this is sort of the new learning, right? This graph is 1/2 to the x when x can be any number. This graph is 1/2 to the n, but we're only taking counting numbers as our x's, right? So we're replacing n because again, that letter n stands for natural numbers. Okay. Questions so far? All right, so I want to do some definitions, and this is again in that same capture sheet. So if you want to open that capture sheet, you should be able to do it in the link that's in the Nearpod. Okay. So a sequence, in case you don't remember from Algebra 1, a sequence is a list of terms. It's a list of terms. And it's usually numerical. In our case, it will always be numerical because we're in math class. That can be finite or infinite. Right, so we could have this sequence, we could have 1/2, 1/4, 1/8, 1/16, and then we stop. And that's the whole sequence. But infinite would be maybe if we continued on forever using those ellipses, right? Okay. So that's what a sequence is. All right, so an infinite sequence is basically this situation here where we keep going, right? So this would be a sequence whose domain is the set of natural numbers. Now again, those are counting numbers, right? Natural numbers start with 1, right? 1, 2, 3, 4, and so on, right? Natural numbers do not include 0. They do not include negative numbers. They do not include decimals. It's counting numbers, like how you start counting, you know, like when you were a kid, 1, 2, 3, 4, okay? So an example of some notation we could use for that is f of n equals a of n equals 1/2 to the n. And again, we use n usually because we're dealing with natural numbers, okay? There are two types that we'll probably look at in this class. Arithmetic, where you have a common difference. And geometric, do you remember what you have with a geometric function? A common, what, anyone remember? It's a common ratio. It's what you're multiplying by. So an arithmetic sequence example would be, you know, you could have 1, 3, 5, 7, 9, 11, right? So all those terms have a common difference of 2. You add 2, add 2, add 2, add 2, add 2. So that's an arithmetic sequence because you have a common difference. A geometric example would be 1, 3, 9, 27, 81, and so forth, because you're multiplying. Your common ratio is 3. Okay. Okay, last definition is the limit of a sequence. Okay, So the limit of a sequence is what we're going to study for the first part of this lesson. So we're going to start with this idea that A of n is a sequence of real numbers. Okay. So we're going to consider the limit as n approaches infinity of A of n. If the limit is a finite number, we'll just call it L for limit, and the sequence converges, then L is the limit of that sequence. Okay. If the limit is non-existent or infinite, the sequence diverges. Okay. All right. So we've basically defined three things. We've defined what a sequence is, a list of terms that can be finite or infinite. We've defined an infinite sequence, which is a sequence whose domain is a set of natural numbers, just keeps going and going and going, like 1/2 to the n. One type is arithmetic, one type is geometric. The one from our warm-up is geometric because it has a common ratio of 1/2. Okay. And then we've determined the limit of a sequence is the limit as n approaches infinity of A of n. And we'll just do some examples on this in a little bit, okay? Does anyone need me to leave this up any longer? Just pipe up in the chat if you need me to leave this up any longer before I go on to the next piece. Okay. So we'll do a couple of examples. We'll do these 4 examples, and I'm going to ask you to participate in the Nearpod and give them a try here. So we have 4 examples here. So determine whether the sequence converges or diverges. If it converges, give the limit. So let's look at part A. So the sequence is 1/1, 1/2, 1/3, 1/4, 1/5. Okay, so again, counting numbers, 1, 2, 3, 4, 5. So the general form, if this is an infinite sequence, is going to be the numerator is always 1 and the denominator is n. Okay, numerator is always 1, denominator is n. So the formula is 1/n. Okay, this is what the graph would look like of 1/x. Okay, can anyone tell me as 1/x, as x approaches infinity, right? As x approaches infinity, what is happening to the function? What y value is it getting closer and closer to? Can anyone say what it's getting closer to? Got some votes for 1, some votes for 0. What y value are we approaching? The bigger n gets, what's happening to the y values? Okay, we've got 0. Yeah, so it's getting closer to 0. So if you have a huge n, this number is going to be pretty close to 0, right? So what that means is that this sequence converges to 0, or you could just write O. Okay. All right. Does that make sense to folks? Like, any questions like about that? The graph is approaching 0 as we get closer to infinity on the x side. So the sequence is going to also approach 0. All right, let's look at B. So B has 2 over 1, 3 over 2, 4 over 3, 5 over 4, and they're nice enough to write the formula for us, n plus 1 over n. All right. So here's the graph, right? So this is a graph of x plus 1 over x. So the limit as x approaches infinity of x plus 1 over x, what y value is it getting closer to? Is the function getting closer to as x approaches infinity? We're getting closer to. Okay, good. Yeah, 1. It's getting closer to 1. So this sequence converges to 1. Okay. You can also tell, this is kind of an aside, but you can also tell by looking at the coefficients. These are the same degree. So 1 over 1 equals 1. Like if you had 2n plus 1 over n, you would take the ratio of the coefficients 2 over 1 and it would be 2. We kind of studied that in Algebra 2 last year and then also a little bit this year. That's how you tell what your horizontal asymptotes are, is if the degree in the numerator and the degree in the denominator are the same, the ratio of the coefficients is going to be your horizontal asymptote, aka your end behavior, aka your limit, right? So that's another way you can tell. All right, great job so far. Okay, let's mix it up. So here's C. We have 2, 4, 6, 8, 10. What do we think? This is 2n, right? Because n is 1, n is 2, n is 3. It's just multiplying by 2 every time. So is there a limit as x approaches infinity of 2x, this graph? Or do we diverge? What's going on? Are we approaching an actual number here, or is it one of those infinity or does not exist situations? Yeah, so people said 3 different things that are all right. No limit, no, and infinite, right? So this is infinity. So this sequence diverges. This sequence diverges. There's no limit. Just keeps going, right? Okay, this is a fun one. -1, 1, -1, 1, and the formula is -1 to the n. And this actually just graphs those counting numbers. So this is funny. Is there a limit, right? So is there a limit as x approaches infinity of this function, we think? If so, what is it? Is there a limit here? And if there is a limit, what is the limit? All right, we've got one person who doesn't think there's a limit. Any other thoughts from y'all? All right, so that's right. There's not a limit. We just keep alternating, right? This is actually called an alternating sequence. So this is also a divergent sequence because we just keep going back and forth. We keep oscillating -1 and 1. We're not really approaching anything. Okay, in this case, that limit does not exist. So the sequence diverges. It has to very clearly approach something. Okay. All right. Any questions about any of these 4 examples? Okay. if you could go ahead and I'll leave this on the Zoom screen so you can refer to it. But if you could go to the Nearpod now and look at the try it, I want to give you about 5 minutes, no, 3 minutes to try this next problem here. So please go ahead and try these 3 problems. Do these sequences diverge or converge? And if they do converge, please give the limit. All right, about 30 more seconds. There are some people who are not in the Nearpod. Can you check the private chat, please? And I sent you the code. Remember also, if you're saying if it converges, please say what it's converging to. Please say what it's converging to. What do you think it's converging to? What number? Okay, I see there's only, let me see. It looks like only 3 people have submitted. A lot of people have not started yet. So I'm gonna give it exactly 1 more minute, but please, if you have not started, please start. And if you're not in the Nearpod, please get in the Nearpod and start. All right, so I'm gonna go ahead and go back to the slides in Zoom. So if you want to check your answers, you can go ahead and look at the slides in Zoom really quickly. So for the first one, we had 1 over 1, 1 over 4, 1 over 9, 1 over 16. You might have noticed that that follows a graph of 1 over x squared. This is the graph, okay? This is what the graph looks like. And we can see that the graph approaches 0, so the sequence converges to 0. Okay? For number 2, we have 1, 4, 9, 16, 25. Some of you might have figured out that that's x squared, but if you didn't, you can see the numbers increase without bound. So this sequence diverges, okay? All right, and then lastly, we have n over n plus 1. Again, that's, you know, you could compare that to the function f of x equals x over x plus 1. And we can see if we look at this function that the limit as x approaches infinity of this function is 1. So this sequence is going to converge to 1. Okay. All right, any questions about the review or anything that we've done so far? Because we're going to move on to something else. I'm expecting you all to basically have a sense of what this is because we're going to move on. Okay, no questions? All right. So I'm going to go back to the Zoom capture sheet because we'll start the next thing. Okay. So this is summation notation. Summation notation. And I'm going to sort of unpack what it means, what it is, why we use it. So summation notation is basically for a sum. So a sum of a sequence is a series. And we use summation notation to basically give shorthand for a series, because I could write out 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus, but then it gets so tedious and you know, you don't want to do that. So this is kind of a shortcut. Instead of writing all this garbage out, we can actually just condense it to a little expression here, okay? So this letter, which kind of looks like an E, is actually a Greek S, sigma. And they use that because it's S for sum, so sigma. So this is sigma, and it just means sum, the sum, right? This little I equals 1 here is just the lower bound of the sequence. So lower bound, and then the N is the upper bound. Okay. And then I is just AI is just the ith term. Right. So instead of writing out, you know, 1 over 1, 1 over 2, 1 over 3, whatever, all the way to 1 over n, we can write the sum from 1 to n of whatever the expression is. Okay. So for example, I'm going to just put a little example here. Let's say I had a sequence that was, or a series, excuse me, a series is when you're using numbers. So let's say the series is 1 plus 4 plus 7 plus 10 plus 13 plus 16. That's a lot to write out, right? So what I might think about is like, okay, well, this is just 3n minus 2, right? Just 3n minus 2. And so I can, wait, do I even have that right? 3n minus 2? Yeah, I do. So this is 3n minus 2. So the formula for the sequence is 3n minus 2. And so I can just say, well, I have my first term, second term, third, fourth, fifth, and sixth. So instead of writing it all out like that, I can say the sum from 1 to 6 of 3n minus 2, right? I can just do that, okay? So that's why we use the notation. So instead of writing out a big long expression of sums, I can just say the sum from 1 to 6 of 3n minus 2. And then that means the same thing as adding these separately. Okay. All right. Questions or anything yet? Okay. All right. So let's evaluate one. So evaluate means find the value. Find the value. So if we have the sum of the first, this means the sum of the terms of 3n plus 1 from 1 to 4, right? So if a of n equals 3n plus 1, that means we need to add a of 1 plus a of 2 plus a of 3 plus a of 4. That's basically what this means, find the value, right? So it's not hard to do, it's just tedious. So 3 times 1 plus 1, 3 times 2 plus 1, 3 times 3 plus 1, and 3 times 4 plus 1. We're just going to add that all together, okay? Right? So this is 4 plus 7 plus 10 plus 13. So 4 plus 7 is 11, 11 plus 10 is 21, 21 plus 13 is 34. Okay. So that's all this is telling us to do, right? That's all this is telling us to do is just expand it out and then add, right? Whenever you see sigma, this is sum. So now we're in series, which is the sum of the sequence. Okay. And then again, we can go the other direction. If we have 11, 15, 19, 23, 27, 31, and 35, how do we rewrite that into sigma notation? How do we rewrite that into sigma notation? So we have to come up with a formula. So what's a of n? Well, let's see, this is an arithmetic sequence, has a common difference of 4, right? So you can make a table if you want, if that makes it easier, right? So your n and then your a of n, okay? So we could do that. We could say, okay, well, let's figure out how we could write this formula. So for the first n, our a of 1 is 11. For the second, it's 15. For the third, it's 19. Fourth is 23, and so on. Okay. I know my common difference is 4 because that's what we're adding each time, right? So my formula for a of n is going to be 4n plus something, right? So let's take 1. 4 times 1 is 4. But then I have to get to 11. What do I have to add to 4 to get 11? 7. Okay. For 2, I know that 4 times 2 is 8. What do I have to add to 8 to get 15? 7. Okay. For 3, 4 times 3 is 12, but my a of n is 19. What do I have to add to 12 to get to 19? 7. Okay, so I think I know what my formula is. 4 times 4 is 16. What do I add to 16 to get 23? 7. Okay. All right. So I think I know what my a of n is. I think I know that my a of n is 4n plus 7. Okay. And I also know that I'm counting 1, 2, 3, 4, 5, 6, 7 terms. So terms from 1 to 7. So writing it in summation notation, I'm going to write the sum from 1 to 7 of 4n plus 7. And that's how you write it. Okay. So we've done both directions. We've done expanding and finding the value, right? Which is just plugging in each index, each number, and adding up the terms. And then we've also done, if you have all the terms added up, how do you write that sum in that sigma notation? Okay. All right. I'm going to leave this up. I want you to try the problems on the Nearpod. There are 2 problems in the Nearpod. Go ahead and give them a try. And we'll go over them in about 4 minutes. Got about a minute left. All right, so I think it's about time. I'll leave the Nearpod open so you can check your work if you want, but I'm going to go ahead and go to the share the. I'm going to go ahead and share my my slides. Kind of take a look at that. So if we review the problem, so the first problem was the sum of the first four terms, 1, 2, 3, and 4, because we start at 1 and at 4 of n cubed, right? So 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, that's 1 plus 8 plus 27 plus 64, which is 100, right? So it looks like most of us got that, so that's great. And then for the second question, from 0 to 5, so that's 6 total numbers, right? So 0 plus 1/2 plus 2/3 plus 3/4 plus 4/5 plus 5/6. So it's about, it's 3.55, which if you do the fraction, it's 71/20, right? Okay, what questions do you have at this point? Anything burning in your brain right now?
So how do you get 71/20?
So if I'm doing this in the calculator, or if you do common denominators even, so I'll go ahead and share the camera. Right, so we know that we have like 1/2 with 0, right? 0/1, which is 0, plus 1/2 plus 2/3 plus 3/4. Make sure I'm doing this right. Plus 4/5 plus 5/6, right? So that's kind of the sum. So the sum is 3.55. And if you're using, working with a graphing calculator, you can hit math 1 or math enter, and it'll end up giving you 71/20.
All right, thank you.
You could also take the time to do common denominators, right? To figure out what, 2, 3, 4, 5, and 6 have as a common denominator and work it out that way, but this is fine too. Okay. What other questions? Okay. Another thing, just the last thing about summation notation, then we'll summarize and you'll do your check for understanding is, so if we expanded each of these sums, so for example, we're not going to expand them all the way, but so for r squared, if we had 0 squared plus 1 squared plus 2 squared plus 3 squared, like let's just go for there, right? So that's 0 plus 1 plus 4 plus 9, right? And then we take, so this is different, right? So here we're starting with 1. So we start with 1. So we start with 1 squared plus 2 squared plus 3 squared plus 4 squared. So that's 1 plus 4 plus 9 plus 16. Or going from 0 to n minus 1 of r plus 1 squared. So if we just start with 0, 0 plus 1 squared plus 1 plus 1 squared plus 2 plus 1 squared plus 3 plus 1 squared. That's going to be 1 squared plus 2 squared plus 3 squared plus 4 squared, which is 1 plus 4 plus 9 plus 16. So sometimes there's more than one way to write the same sequence, right? This and this are basically giving you the same thing, right? It's just that we're shifting everything to the left one, right? We're starting at 0 instead of 1, and then the formula is r plus 1 squared, right? So just that takeaway is that there's more than one way to write a summation notation. Okay, so I just want to make sure that you all have that idea kind of in the back of your minds. There's more than one way to write a series in summation notation. It's not just one size fits all, okay? All right. Any other questions or anything right at the moment for me? Okay. great job. I appreciate especially people who are really trying and finding creative ways to get this done. This is awesome. Really nicely done. I'm going to go ahead and summarize and then move you to your exit card. It's a little bit of a longer one today, which is why we're taking so much time with it. All right, so in summary, what we've learned today is that we can find limits of infinite sequences by recognizing the end behavior of the underlying function. So that was the first part of the class. And the second part of the class is that we can use summation notation to describe a series. Okay. All right, so I'm going to push you forward. There's a link to the check for understanding. So if you click that link to the check for understanding, it should take you to today's exit card. So you can go ahead and answer the questions as best you can. And it might take a little bit longer. So when you're done, you can log off, okay? So good luck with the exit card and let me know if you have any questions.